Okay, welcome back. Today we're going to cover the topic of reflection and transmission of waves, and then the theory of it first, and then I'll apply that to the example. Remember last time we were covering chapter 16, we covered a single wave and what happens to it, and we covered this equation y of x of t is equal to a sine of kx minus vt plus phi. And then we did lots of different problems with it. We analyzed the motion of this wave. We analyzed what it meant, and we applied that to different examples. So today I'm going to cover the theory of what happens to this traveling wave when it meets a certain boundary, when it reflects from that boundary or transmits into that boundary. So let's first cover reflection. So let's say a wave is coming like this. And let's say it is connected with a hook like this, and let's say the boundary that the hook is connected to is like a wall. This is called a rigid boundary. A rigid boundary. So there's a little hook here, and then the rope or string is connected to the wall, and then the wave is coming like this, traveling like this. What will happen? What will happen to that wave when it reflects off the rigid boundary? The answer to that is that upon reflection from a rigid boundary, the wave will experience a phase shift of 180 degrees or pi radians. So if the wave is coming and it comes as a peak, then upon reflection, the wave will turn into a trough. That's what it means to say 180 degree or pi radian shift. And this is true when it bounces or reflects from a rigid boundary. So a peak becomes a trough. And then it goes back like this, completely opposite like this, traveling back. Of course, if the incoming wave keeps coming in and reflecting off, then you will get what's known as standing waves, and it will interfere with itself. But in this chapter, this is chapter 16, we will not cover the topic of interference of the wave. So let's just assume that the wave is coming and then reflects back, and then the wave doesn't just keep coming after that. Okay? So we'll focus on the reflected wave and the nature of the reflected wave, not so much the interaction of the reflected wave with the incoming wave. This is the incoming wave. And then this is the reflected wave. Okay? So we'll focus on the reflected wave. So we learned that there's a 180 degree or pi radian shift. And of course it travels backwards. So if the wave is coming to the right and it's traveling to the left, so what happens? How do we correct the equation then? What happens to the equation? Well, if the incoming wave is like this, incoming wave, then the reflected wave is going to look like this, a sine of k. So then we're going to have to say x plus vt, right? Why? Because it's moving to the left. Remember, a wave that is moving to the right, this is a minus. If the wave is moving to the left, then this turns into a plus. So if you forgot that, you can watch the original videos, the first set of video that I did in chapter 16 that covers the nature of the wave. Then the phase angle of the wave is phi, of the incoming wave, but then I have to add pi to it to correct for the shift of 180 degrees. So pi radians, or I can subtract. I can either add pi radians or I can subtract pi radians. Either, it doesn't matter. So then this becomes the equation of the reflected wave from a rigid boundary. So now let's see what happens to the wave from a non-rigid boundary, a boundary that is free to slide. So that will look like this. So a non-rigid boundary So the wave will look like this, and then you'll have a hook, and maybe there's a bar here, like a post. And so this hook is free to slide along the bar. For a good demonstration of this, you can go to my demo playlist, and I have a demo playlist of different demonstrations, and I've actually demonstrated this. I've demonstrated a case where a wave comes and hits a rigid boundary, reflects back, and there's a 180-degree shift. And I've also demonstrated a case where it hits a non-rigid boundary, it's free to slide, and then you can see in the video that when the wave reflects back, it does not experience a phase shift at all. So an incoming wave goes like this, and then let's say the peak of the wave comes like this. And so since this is free to slide like this, what's going to happen is that it's going to hit the rod, it's going to slide, and upon reflection, it's going to come back with the same phase. So a peak coming in will bounce back with a peak, and then the only difference is that it's going to move to the left. So this is a slidable, non-rigid boundary. And then so it just comes back like this, no phase shift. No phase shift. Okay? So then how do we write the equation of that? Well, the equation doesn't change much except that you just add a plus to the velocity, right? So the reflected wave in this case, reflected wave is going to be a sine of kx plus dt plus phi. So if the original wave has a phase angle of phi, the phase angle of the reflected wave will also be phi, but it will be moving to the left, so it will we change that to a plus. So that's the only difference, that's the only change that we make in that case. Okay? Later on, when we cover the topic of optics, much later on, I plan to be doing videos on optics, you'll see that this is also applicable to the field of optics and wave interference. This is called thin film interference. So if you have a light that comes, this topic is called thin film interference. So a light wave will come, and let's say you have a layer of oil. Let's say this is a layer of oil, and then let's say this is the ground. So there's a layer of oil on the ground, and then the ground is below that. So what's going to happen when the light wave comes and reflects from the air to oil? In that case, since oil's index of refraction is bigger than air, it's considered a heavier medium than air. So it sort of takes the same role as a rigid boundary. Okay? So compared to air, the oil acts as a rigid boundary, and upon reflection from the rigid boundary, you experience a pi radian shift. So it goes back like this, and then you have here pi radians shift. So because it's considered a rigid boundary, right? The other way to say pi radian shift is a shift of half of a wavelength, right? Because a complete wavelength is 2 pi radians. So pi radian shift means half a wavelength of a shift. So a peak becomes a trough becomes a peak. So that's a shift of a half a wavelength. So we can say half a wavelength, lambda over 2 shift, here at the air to oil. Then the part of the light wave transmits into the oil, right? The other thing we're going to cover here is what happens when the wave comes from one string and then connected to another string. So that's also the same topic. What we're going to see is that when a wave transmits from one medium to another medium, there is no shift of pi radians at all. It doesn't matter from lighter medium to heavier medium, or from heavier medium to lighter medium. The transmitted wave never has a phase shift. So part of the light wave will go inside of the oil. It will have no phase shift. Then there's going to be a reflection from the oil to the ground. So the ground, is that a heavier medium than the oil? It is a heavier medium, right? It's a very rigid medium. Light cannot penetrate it at all. So we say that the ground is heavier medium than oil, and upon reflection from the ground, there's also another pi radian shift, right? So we say pi rad shift, or lambda over 2 shift. So then it goes back, reflects back, and then it transmits into the air, right? And then from oil to air, since air is lighter than oil, well, it doesn't matter. Transmitted wave has never a phase shift. Heavier to lighter or lighter to heavier, it doesn't matter. So this wave that transmits into the air also has no shift. So then these two waves come, and then if you're looking at it with your eye, they're gonna interfere with each other, those two waves. So what happened? Upon reflection from the top medium, you have a half a wavelength shift, and then upon reflection from the bottom medium, you have another half a wavelength shift. But then, are those waves in coherence with each other? Well, half a wavelength and another half a wavelength is like a complete wavelength of a shift, right? Together. A complete wavelength shift. A complete wavelength shift is like having no shift. That means the peak turned into a trough, the trough turned back into a peak, so you have two peaks. Then what we're going to argue is if the extra distance that this traveled in here, if the extra distance, because this wave traveled an extra distance, right? This is the thickness of the oil, so then we're going to say twice the thickness of the oil, the oil's thickness, we're calling it T. If twice the thickness of the oil is equal to some integer times the wavelength of the wave in the medium, so this is the wavelength of the wave in the medium, lambda prime, right? And then we're calling this integer m. So we say twice the thickness of the oil, if that's equal to an integer multiple of the wavelength of the wave in the oil, in oil. Then these two waves will constructively interfere. This will give you constructive interference. Right? Now, what oil ground, you have air, let's say this is a soap bubble, you know. So you have, let's say, a thin layer of soap, and then you have air, right? So then you have light comes, reflects, you have a half a wavelength shift. So then it transmits, but transmitted has no shift. So then it comes, right? Then it reflects. So now, soap, air. Air is a lighter medium than soap. Upon reflection from the air, it's kind of like the movable rod, the string wave experiences no phase shift. So the one here experiences no phase shift, right? No phase shift. Then it comes back and then transmits. And then what's the condition for these two waves to constructively interfere? So we're going to say twice the thickness of the soap bubble, 2 times the thickness of the soap bubble, if that's equal to an integer multiple plus a half times the wavelength of the wave in the oil. Or in the oil, or we can say the soap. Now, how did this change? Why is that different? In this case, I put n, and m is basically any integer. 0, 1, 2, 3, 4, 5. This is the condition for constructive interference for air, oil, ground type of situation. This is the condition for constructive interference. Constructive interference for a type of situation where you have a lighter medium, heavier medium, and then lighter medium. Okay? So why is there this extra half? and then you got m equals 0, 1, 2, 3, 4, and so on, right? Why is there that extra half? Well, because the wave that reflected from air to soap experienced a half a wavelength of a shift, but the wavelength that reflected from soap to air experienced no shift, right? So one of the waves is already a trough, the other wave is a peak. So what's the condition for these two waves to interfere constructively? Well, the extra distance traveled by this wave that goes to the bottom, that extra distance, which is twice the thickness, must be equal to some integer, which is, let's say you can put 0, and then half of the wavelength of the wave in the soap, right? If it's half, because one of the waves is already a half off from the other one, right? It's already peak and a trough. If they're off by a half, then these two waves come here and they both become peak, right? And they constructively interfere, or they both become trough and they constructively interfere. So this becomes an extra half, and this one does not have that extra half. So this is the topic of reflection transmission that we're studying in chapter 16 with strings and waves in strings. We're applying it to electromagnetic waves hitting a certain film, and this topic is known as thin film interference. So now let's talk about the transmission of the wave, right? So this is a thicker string, this is a thinner string. So an incoming wave comes in, right? An incoming wave comes in, and then at the boundary, the wave transmits, okay? What usually will happen if this is a thinner string than that, most of the energy of this wave will reflect, right? It will reflect, but part of it will transmit. Maybe let's say 70% will reflect, and then 30% will transmit. We can say that 70% of the energy of this wave reflects back, 30% transmits. What happens to the reflected wave? Well, if this is a thicker medium than this, this wave, it almost acts like a rigid boundary, right? Because in comparison, this is thicker than that, so it kind of this acts like the wave in the electromagnetic wave in air, and then this acts like the electromagnetic wave in soap or in oil, right? Because this is a thicker medium, and the index of refraction of oil is bigger than the index of refraction of air, right? So upon reflection, you have a pi rad shift, right? 70% of the energy of the wave, let's say, reflects back. It all depends on the mutual densities of the two mediums. What portion of the energy reflects back? Okay, so for now I'm just saying 70% or maybe 80% or something like that. 30% transmits. So what happens to the transmitted wave? The transmitted wave never experiences a phase shift. So if this is a peak coming in, simply just going to continue traveling as if there was no boundary over there. So this peak would have come in right there, right? And if this thick string happened to also be a thin string, right? It was just a simple thin string, so the peak would come in, and then nothing would happen to it. It would be just simply, it would continue going, becoming a trough, and then going up, becoming a peak, right? So at the boundary, that's what should happen. It should just continue. If it's a peak here, it should just continue, and it should go down, turn into a trough. So it should just continue gently as if there was no boundary at all. So you shouldn't even feel like there is a boundary for the transmitted wave. So we can say no phase shift for transmitted wave. Okay, now let's do the opposite. Let's do a thick string like this. Okay, so this wave is coming in, this wave is coming in, and then we do a boundary. And you can also see this in my video playlist where I've illustrated how the waves reflect off a boundary between two different mediums of different densities. So I also have a demonstration with that. So then what's likely to happen here, most of the energy of the wave should transmit, right? Because since this is a thicker medium, maybe again 70% transmits, and then maybe 30% reflects, right? 30% of the energy of the wave reflects. So what should happen from the reflected wave? Well, in comparison, this acts like a lighter medium to that. So it acts like the movable. It's almost acts like that movable rod. So this one acts like the electromagnetic wave in oil, right? And then this acts like the electromagnetic wave in air. So then upon the reflection, there should be no phase shift. So it goes like this. So if the peak is coming in, the peak should basically go back out. So it's just no phase shift. We can say here, no phase shift. Peak is coming in, peak will come out. If the trough is coming in, trough will be coming out. Okay, how about the transmitted? Same thing as here. It's as if there was no boundary, right? So if the boundary is here, it's as if there's nothing. So the wave will just come in, simply just continue going. Go like this, go like this, go like this, like that. So if there was a phase shift, what would have happened is the wave would come in, and then at the border, it would all of a sudden jump back out like this. So there would be almost like a noticeable shift. It would come in like this, and then the peak should eventually turn into a trough here. But if there was a phase shift, the peak would come in, and then it would turn back into a peak. And that's what would look like a phase shift. So if you see my video, you will see that that doesn't happen. It continues to go, and then it continues to just continue on its path regularly as if there was no border at all. So now let's apply this to a problem with an example. Okay? Thank you.